Yeah, great. Thanks for pointing it out. Okay, so for a given accuracy of the relative accuracy of the calculation, you derive that in Euler, the required time steps was square root of r over, or the relative time steps, over 2 pi in RK2 for the midpoint method. It was 1 over square root of 2 pi r to 1/4, and in RK4 it was sort of a more complicated expression with 2 powers, but let's take the first term. So it's about roughly comes out to be 1.01 over pi r to power of 1/6. There is another term of r to the power of 1/8. And when you plug in the number, you get that the ratios are about 1 to 5. Where do I have it here? Yeah. Okay. Yeah, the ratio, the Euler, if I call this, let's call it 1, so that was about 1/5 of that, and that was a further factor of about 1 over 25. Now, so that was in question 2, so that was fine. So you derived it analytically, so that's nice. Now, in question 3, you were the target was to calculate for a total time of 10 times the period. So that's the period. So to calculate the orbit now with a requirement of a precision of what I call the total time. So that was for a single step. And now we require that the integrated order, the accuracy over this time would be, again, 0.01 or 1%. And the result was that in Euler, the number of steps required, so the question is, what is n that you need to this to reach this precision? So to get that, what is n? And so with the Euler, so the result was that n is about 395,000 steps. With RK2, it was 729. The exact number, you don't have to get this exact, but order of magnitude or roughly. And with RK4, the n came out to be about 157. Now, I didn't ask in the homework, but when you think of it, it seems very strange that to reach the given precision in a single step, the time step in RK2 is a factor of 5 smaller than Euler. But when you look for a more extended integration, you see that you need 700 time step instead of about 400,000. There is a huge improvement. So if I call it n Euler and R K2 and NRK4. So now the ratio is about 500. So this is 500 times smaller. Here it is about a factor of 5 times smaller. So it's smaller than RK2. And this is about 500 times smaller than Euler. So the time step is 5 times smaller, but the total steps we need is a factor of 100 yet smaller. So how come you get such a huge improvement even though the time steps is only a factor of 5 smaller? So this, so what? So this should have, I think, surprised you. And did you think, or what do you think is the reason for that? Any idea? No idea. Okay.
Increasing the number of steps.
Yeah.
We discussed this before, that increasing the number of time steps makes the time step smaller, and so the error in each time step is smaller, but it also increases the number of time steps and errors compound with the time step. So
right, exactly. So we have the errors accumulate. So so let's see it. Let's derive this number and see it quantitatively. So answer the question quantitatively. Why do we get such a huge improvement yeah, generally. So, okay, so let's see it a short derivation. So or let's basically calculate n, the required number of steps. Steps. So in question 3, which is okay. So okay, actually I wrote it here. You derived it sort of experimentally by running the calculation, but one can do it also analytically. So in principle, the number of steps is the total time, which is 10t over the time steps, over the delta t. Okay, now, yeah, the per step, we know we have this relation here. The requirement now is on RT, on the total, that we required it to be 0.01. We know, on the other hand, that the total, since the errors add up, so the total error is n, the number of steps, times the error on one step, r. So, so r is RT over n. So this is the required precision per step. Okay, so that's very simple. On the other hand, we know we can take from here the relation as we know that the derived, from here, we get that R is 2 pi delta t over t squared. So this is the relation of the precision per step and the time step size. So we can compare this expression to this expression. And so this is RT over N, and N I take from here. So it is 10T over delta T. So this way we get now an expression for the step size that we need. Okay, so so from this equation we get that delta T over T is RT over 10 times 2 pi squared, so it is 4 pi squared. And so this is the time step, and the number of steps is 1 over is the total time over delta t. So we take the inverse times 10, so we get that it is 100 times 400. So it is 400 pi squared. Over RT. So this is 0.01. So it's 395,000 steps. Okay, so that's what Euler gives. Now let's see what we get for RK2. So this is the same derivation, same expression. What is different now that the relation between the precision and the time step is now different, because we now use this expression, delta t over t. So R, based on that, is now so it is delta t over t square root of 2 pi to the power of 4. And this equals, again, what we have here on the right-hand side. So this is RT over 10t delta t. So now we get that delta t over t is RT over 40 pi squared, all of that to the power of 1/3. So N would be again the same. So N is 10t over delta t. And now we take t over delta t from here, and so it is, we can write it down here. So N is now 10, and t over delta t, so it is 10, and now 40 pi squared over RT to the power of 1/3. So see the difference from here. In Euler, it was the 10 is Also here we can write it as 10 times 40 pi squared over RT. And what we have here is that this expression now is to the power of 1/3. So that comes out to be 10 times, actually, 39,500 to the power of 1/3. So here it was linear with this number. Here it is to the power of 1/3. So it comes out to be 729. So the reason for these huge differences is the relation between the precision and the time step. Here in RK2, if you reduce the time step by a factor of 10, you improve the precision by 10 to the 4. In Euler, it's just linear. And here it is actually goes to the power 4. And so you need the total, the demand of R is much smaller. And therefore, delta T can be much larger. And if you go to RK4, then R, we take, it would be from here, let's say this is a roughly 1. So, yeah, that's one side. So you get that, sorry, here there is a 2 pi. Okay. So this roughly cancels with the 2. So R is now roughly delta T over T times pi to the power of 6. So what you get that N would now be 10. And this, what we had here, so we have here 10 pi, 10 over RT, 10 pi over R. So this to the power of 6 over 5. And yeah, maybe I write it this way. It's 10 over RT to the power of 1 over 5 times pi 6 over 5, and this is 157. So basically now the precision now goes like delta T to the 6th power, or the step size goes like the 1 over 5. So 1 over RT to the power of 0.5. So what we see here, that initially we get a huge precision because of the increased or huge reduction in the number of step size for a given precision, comparing Euler to RK2. From RK2 to RK4, we still get a significant reduction. Now the question is, should we, or do we gain much by going to higher precision schemes? Let's say go to, we can think of RK from RK4 that we have here, maybe go to RK8 or whatever. So what do you think? Is it worth going to higher precision schemes? Yeah.
Young wrote no.
Why no? So no is the correct answer. The question is why? Why? I mean, it's not, or...
It's also not easy. I mean, from RK4 to RK8, you need to also contains a lot of calculation, and just to reduce some sort of steps here is not really, how to say, efficient.
Yeah, exactly. So what would happen is that the gain what we have, let's say we have, it would go from 1 over 5 to 1 over 7 or 8 or whatever. So this is not going to get larger by a significant factor compared to what we hear here, that we take a huge number of about 40,000, and taking its square root, you reduce it enormously. Now you take the 4th root, so it went a bit more low. If you take the 6th root or the 10th root, it's going to actually asymptote close to about unity. The improvement are not going to be so drastic by going to higher precision scheme, but on the other hand, what is the price for going to higher schemes in terms of the calculation or the code?
Each step takes more time.
Yeah, exactly. You need, actually, the scheme, we saw that in RK2 there were 2 terms. In RK4 there are actually 4 terms, and each term you need to calculate. So actually, the number of steps now goes up linearly with the order of the scheme. So you make it 8, so you need now 8 terms. And so it's going to take, each step is going to take at least twice as long compared to RK4. So the gain, so actually in terms of scheme, the gain becomes small, and actually the routine itself becomes, the algorithm becomes longer. So in many cases, or what practically happens is that RK4 is commonly taken as the best or the sort of best compromise. You shorten the integration time by a large factor. The scheme or the procedure didn't develop and become too elaborate. And this is called what is called sort of the sweet spot or the optimal scheme. So this is sort of, I would think, the working horse method for solution of ODE is to use the RK4. And personally, I think it's better, the better version is what I always use is the RKQC on numerical recipes book. And this is the adaptive step size. So if in your specific physical problem, you expect to get significant changes in the relevant time scale, then this is would be really the standard numerical scheme. Yeah, so this sort of almost finishes the ordinary differential equations. In terms of the solution scheme, this covers almost anything. So I'll touch now another aspect or difficulty that it's actually can happen a lot, and when the solutions are unstable. So we'll see an example. And there is what we call implicit schemes to handle these problems. Okay. Next step. Okay, so I'll call it implicit schemes. And it's also called another way of calling it is a stiff set of equations. And it's more, you can see more of it. I'm not sure exactly how much there is in Garcia, but I followed more numerical recipes. So it's an R 15.6. That's on the second edition. Okay, so the idea is that the situation that we want to handle here is what we have unstable solutions. So this occurs for, it's not always, but there are more or it characterizes or rises some equations. So let's see an example for a specific equation, ODE, which is likely to be unstable in terms of the solution that we derive. So an unstable solution would be that if this is the, let's say, the analytic solution, that we want to derive, and so let's say this is x as a function of t, and we have some initial condition here, it's some t0 and some x0. We have some f of x, and we want to derive x of t, f of x plus some f of x0. So we have x 0 at t0, initial condition. And what we would see is that initially it sort of follows the equation, but then you start to have a diversion. It can oscillate or it can just go away from the solution. So it can be something like that. And when it's an unstable solution, it means that making the time step in this here, delta t, smaller doesn't help for long enough total time, t. So that's the nature of instability, that once something is unstable, then you just cannot get over it by just forcing the time step to be small. Or it can be extremely expensive to try to keep the time step small, but when it's unstable, it's just unstable and you are stuck. You have to find, you cannot by brute force taking the step to be small enough and make it stable. So let's see some example why this happens. So let's take the differential equation that y double dot is 100y. Okay. So So this is the ODE that we have. Okay, so we know the equation is that if we look the analytic solution, is that y is a e to the minus 10x plus b e to the power of 10x. So this is the general solution. Now, if we take a given initial condition that y of 0 is 1 and y dash of 0 is minus 10, then sorry, this is 1. Okay, so so this tells us that e to the power of 0, which is 1, plus b equals 1. The derivative here is minus 10 so this gives us that minus 10 a plus 10 b is minus 10, or we can cancel that. So the solution is, take a simple case that a is 1 and b is 0, 0, and the solution is that y is a e to the minus 10x. So everything here is just analytic. But if we are given for for a more general initial condition, then it could be given that y of 0 is 1.365 whatever, and y dash of 0 is minus I don't know, minus 26.356 and so on. And I didn't check the numbers, but let's say that it was supposed to be the same solution. But now the numbers are not really exact because we have finite precision. So when we solve it, so we have here finite precision. And so for the solution will be now that y will be e to the minus 10x, sort of the true solution. A is 1, so this is the solution, 1. So e to the minus 10x plus some epsilon e to the power of 10x. So this is just because of the round of errors in the initial condition. So there is a very small error, and this can be, let's say, maybe 10 to the minus 16 or 2. Okay, that would be really as we learned, this is the smallest number you can get. Let's say it would be 10 to the minus 10. So what would happen to the actual solution when we go to a large enough x? What will dominate the solution?
The solution we got from the round of error, the increase in exponent.
Yeah, exactly. So this is, if we plot the solution, y is a function of x. So we start, let's say, we said 1.36 or something, 1.36, whatever. So initially, it's going to be to follow this exponent of roughly e to the minus 10x, but it's going to get closer and closer to 0. But then, for a large enough x, this is going to always dominate, regardless of how small epsilon is. And so so actually, it's going to diverge exponentially. So this is when the e to the epsilon times e to the 10x will become dominant. So that's, I mean, in the analytic case, we took this very simple initial condition, but this is not what we generally find. And this round of error leads to this divergence. Yeah, so let's look how we can get over this difficulty. Okay. So we can represent it as a more general, or let's say our ODE. Let's write it. A general form for the ODE is that, let's say, y tag is minus cy. So again, it would be an exponential solution. So yeah, so that leads to a solution that y is a e to the minus, sorry, cy minus c times 1. So e to the power of minus cx. So that's our analytic solution. If we now look at the Euler scheme, so a y n plus 1 is yn plus h times y dash n. So this is the step, or in x. So this is yeah, x. Yeah, this is delta x. Yeah, okay, so we can see that if we plug in the equation into the Euler scheme, so yn plus 1 is yn minus c times h, or h times c yn. So it is 1 minus hc yn. So this yn plus 1. So if generally, if a 1 minus HC is smaller than minus 1, so we're assuming HC is positive, so this cannot be larger than 1, but it can be smaller than minus 1. Then obviously solution diverges. So this is very sort of a trivial case where each element is going to be larger. So even though we know that the true solution actually converges, because it always decays. Yeah, so it means that we don't want to avoid this divergence, so we need so the condition is that we want that 1 minus HC to be larger than minus 1. To avoid that, so H over C should be smaller than 2, or the time step H should be smaller than 2 over C. So it means that we need the time step to be small compared to this C, which is basically the exponentiation length scale. So this is, to some extent, this example is so a bit extreme, because if this is, the solution, so it decays on, let's say, it goes from the initial solution to, let's say, y0, and here it is y0 e to the minus 1. So this is the length scale, which is 1 over c. So this is, let's call it delta, at which the solution goes to 1 over e of the initial solution. So you don't want to use a time step which is larger than this exponential drop time step. And so that's, this example is somewhat trivial, because you would obviously don't want to use such a huge time step when you solve such an equation. But it just shows the demand in principle, that it's going to be unstable. Okay, so now let's look at the implicit scheme. So implicit scheme, which would actually work for any time step, just the accuracy would not be good, but it's going to be stable, is to write the difference equation. So we write the difference equation as the following. Instead of this one, we write that yn plus 1 is yn minus h c yn plus 1. So we actually calculate, or can do one step before that, is that generally that yn plus 1 is yn plus h y dash n plus 1. So we take the derivative sort of at the second stage, at the following stage. So for this differential equation, this translates to this equation. And so let's see why it becomes stable, because now we can, what we get is that yn plus 1 times 1 plus hc is yn, or yn plus 1 is now yn over 1 plus hc. So instead of having this equation, we have this one. And now you can see that there is no problem with h. We can make or the solution would always converge. So this kind of scheme, it doesn't diverge even for like it for h as large as we want. So the next step is always going to be smaller than the previous one, the next value of the function. So it's going to go down. It's not going to be accurate, but it's not going to diverge. So there is no limit on the time step. So it's called implicit because, or why is it implicit? Because sometimes we had this very simple ODE, which is just linear and simple ODE. But what do we do if, for example, what if y dash is, for example, sinus y? Okay, so we can have this differential equation, and so in terms of the difference scheme, what we will have here is that yn plus 1 is yn plus h sine of yn plus 1. Okay, now we move it to the right, to the left, so as we did here. So now it's going to be that yn plus 1 minus h sinus yn plus 1 is yn. Now we want to derive yn plus 1 from the previous step. So here it was simple because it was just a linear equation, so we could get a clean expression for yn plus 1. But now on the left-hand side, we have this implicit, so this is now, we have an implicit expression for yn plus 1. So what do we do here? So what do you think? So you write the code, and in your code, you have this line that you now need to find that yn plus 1 equals something based on this.
Maybe for a small enough h, you can use Taylor for the sign, and then you give up some accuracy, but well, it depends on your step size, I guess, because for large step size, you can take a Taylor of sign, because then yn plus 1 maybe grows rapidly, but I don't know how to find the balance between them.
No, but excellent. This is exactly the right attitude, because indeed, we are going to use generally a small time step. The h is going to be small because, as we discussed a few times, when you integrate your equation, you want to make steps which are that in each step, your solution changes by a small amount. It's sort of a built-in requirement to reach a high precision. You don't want to make steps where the function changes significantly, because then the derivatives also change and we have all the problems that we discuss. So it's a built-in requirement for high precision is to use a situation where yn plus 1 changes almost slightly or by a small amount compared to yn. So indeed, we can just use Taylor expansion and write it this way, that our or basically another way to describe it, we can linearize the ODE.
But Ari, will you take the Taylor expansion of yn plus 1 around 0 or around yn?
Around yn, of course. So I write it down. So we can take our f, which is a function generally. The differential equation is a function of x and y. So this is y dash. So we can write it as f of x, that's n plus 1 and yn, and df dy at yn and times yn plus 1 minus yn. Yeah. So we describe f of x and y as these expansion, the first two terms in a Taylor expansion. So this this expression is what we take as f of xn plus 1 and yn plus 1, which is what we have here on the right-hand side. And these, we can actually take the derivative of f with y. We have this expression for f of x and y, and calculate it at yn. And this is now the difference in the solution, which is unknown, but we can calculate these coefficients. So let's call this thing A. We can calculate this derivative at y. Let's call it B. So basically, we write the differential equation. We equals as A, some constant, plus B, yn plus 1 minus yn. So basically, we turn it into a differential equation, which is now linear with y, rather than a sine, for example. And so with this expression now, in the implicit scheme, yn plus 1 would be yn plus h times f, or a plus b, yn plus 1 minus yn. And so eventually yn plus 1 would be yn 1 minus hb over 1 h8, I think, 1 minus b I have some mistake here. This should be yn plus b. Ah, yeah, okay, it's good. No, sorry, it's hb. There is an a missing. Here it is hb yn. H. Yeah. Okay, never mind. So, okay, sorry. Do it, so this yn plus 1 plus or minus. And here we have h, b, hb. Okay. On the right hand side, we have yn, 1 plus hb plus ha. Okay, so from here you get that yn plus 1 is, so we turn it back to a direct expression. Another option is actually to solve this kind of equation. You can also solve it another scheme.
Ari, can we take a break?
Yeah, just finish that. So another solution scheme is just iteration. So how you solve it by iteration? Yeah, you can, you basically derive, let's say, you have an expression that, for example, x, if you have that x plus or minus x minus a minus x equal 0. So how can you solve this equation by iteration? What is the iteration scheme?
You put some value, you check it, and if x is larger than the other one, then you, I don't have it exactly sorted out, but you do a check and then you put some condition that you should lower your guess or raise your guess by its value.
Yeah, so in principle that's correct, but it's actually in this kind of situation, it's even simpler because on the one hand side, we have y itself that we are looking. So this is, in this case, the x. And then we have something more complicated. So the more complicated is the sign plus this constant here. So how we solve it? We actually need to solve the equation that x equals e to the minus x. So how we do it by iteration? We first guess a value. Then let's say 0. So guess a value, let's say 0. So this is the value that we guess, and this is the outcome. So we guess a value, plug it in. So this is the outcome. So we put a 0 on the right-hand side for the right-hand side. we put 0, so what comes out to be x?
1.
If we if x is 0, what x actually comes out to be?
Should be 1 if you raise it.
Exactly. Guess a value for the right hand side. Guess a value for x. We put the value here, so it is e to the minus 0. So e to the minus 0. So the outcome is 1. So now we put this new value here. So e to the minus 1 is actually calculated. So it's 0.367, whatever. Now we put this revised value that we derived here, 0.367. So, and that comes out to be, e to the minus 0, whatever. Yeah, so e to the minus 0.367 comes out to be 0.69922. Then we plug it in and get here another number. So you get the idea. And what is that within 5 iterations, you can get a result which is 0.5675. You get something which is accurate to about 10 to the minus 4, something like that. So it's really can be really simple. It's not always that it converges so quickly, but that can be just a sort of a numerical trick. Okay, so let's take a break and return in 10 minutes. Okay, so are you with me? Anyone?
Yes.
Okay. So one last word on this implicit scheme is that we described it in the Euler scheme, but we can also have it implicit scheme. We can have it in second order. So we can write that yn plus 1 is yn. And now we take the midpoint or the average. So we take y dash n plus 1 plus y dash n. And so for the specific case of y dash minus cy, we get that yn plus 1 is yn plus h over 2. Yeah, actually minus hc over 2 yn plus 1 plus yn. So this gives that yn plus 1 is 1 minus hc over 2 over 1 plus hc over 2 yn. Okay, so you can you can in principle work it out in higher scheme, but that's you know the direction. Okay, so I can erase it right away because you can always look back at the video. And so now let's go to the PDEs. So I'll go to PDE 1, which is chapter 6 on Garcia's book. Yeah, so we can write it, it can be some in the form, some function of x and y, or x and t, or can be a function of x, y, z, and t, and so on. Now, when we look at the trajectory of a particle, for example, we can have a differential equation of the form, which is a function of also position time. And so let's take that this is would be the acceleration of a particle. Acceleration, for example, under gravity, harmonic motion, or whatever. Now, this is also a function of x and t. Why this is not? Why? This is not P, D, P, D, even though it's a function of position and time. So what is the difference between this and this one? Okay, so that's a very, very basic and important question. Very simple also, when you know the answer. It's not really complicated.
X depends on t in fx t equals x. So actually, there is only one variable. One independent variable.
Exactly, exactly. Because here, x is the position of the particle, which depends on t. And this is what we are trying to find. What is x of t? This is what we are trying to solve. But only t is the independent variable. Here, all of these are independent variables. So these are just the coordinate in space. And this is sorry, these are the coordinate space, and this is the time coordinate. And so these are PDEs actually are designed when we have more than one independent variable, or in other physical terms, more than one coordinate. So it's basically a differential equation which describes things which change with position and time, or quantities that depends on both position and time. So the examples so we can have the heat diffusion. Diffusion equation. So the temperature is a function of both position and time. And the heat diffusion equation tells us that the time derivative of the temperature, which is a function of position and time, is the Laplacian of the temperature. So in 1D, it's dx squared of t of x and t. So we have two coordinates, both position and time, and this is the heat diffusion equation. We can have the wave equation. Wave equation that the second derivative in time is some coefficient, which is the velocity square, square, and so this is the amplitude wave. So this is the temperature, which depends on position. So this is position. This is time. And this is the wave amplitude. Which is, again, also function of position and time. And another example is electrostatic potential, or static potential. Now, because it is static, we write it as phi of, let's say, x and y only, of position only. And so the equation is that the the Laplacian of phi is 1 minus over epsilon f as the charge. So these are, so actually most of the action in physics is described by PDEs. These are quantities which depend both on position and time. The 1D are much more, the ODs are much more limited. And as you probably took the course in PDEs, so to remind you, the PDEs are classified. PDEs, they are named either a hyperbolic or parabolic or elliptic based on the, if we write generally a PDE in the form that it is yeah, okay, never mind. You can remind yourself. This is classified as a parabolic equation. Depends on the coefficients and the wave equation. Yeah, so the wave equation is hyperbolic. And the Poisson equation, so this is Poisson. So this is elliptic. So these are just naming, but there are different numerical solution scheme, as we will see for these different families of PDEs. Yeah, so once you go to PDEs, there is no RK4 that solves everything. So it becomes much, much more evolved, and the schemes you cannot run such a high precision scheme, and it can be challenging, but there are problems that can be solved. Okay, but it's much, in principle, it's much more involved than PDEs. Okay, so what we need, of course, if we want to solve a specific equation, what do we need in addition to just the equation itself?
Initial conditions and or boundary conditions.
Exactly. So let's see. So now the initial condition, boundary condition will now be in 2Ds, because now we have both coordinates in space and possibly coordinates in time. So we need initial condition plus boundary. So it's the same thing, but this is, when we talk about boundary, this is in space, and the initial, this is in time. So the boundary in time is the just initial, it can be final, but usually it's less used. So we can now describe the coordinates. And maybe I'll replace this, just a bit. Yeah, so this would be position in space. This would be the time coordinate. So there is some region, let's say XA to XB, where we are looking for the solution. So this would be the initial condition. And then we'll have the boundary, the values at XA and at XB. So the initial condition would be what we have here is X at, sorry, the function that we are A, let's say. So we have, this is the PDE. So this is A as a function of X at t equals 0 for X in the solution regime between XB and XA. And this would be A of XB in T and A of XA in T. So, so this is the initial condition and the boundary condition on this and this. Okay. Now we can also have when we have the boundary condition, this kind of condition are called the Dirichlet condition. So if the boundary conditions are on A, then this is called the Dirichlet conditions, Dirichlet boundary. But it can, instead of A, it can be on the first derivative. If we are talking about second derivative, PDE, then we need a boundary condition on the first derivative. If they are on the condition on the gradient, so if, for example, the X at, let's say, X A is some function of T now, and on the other side, XB is some other function of T. So these are the Newman boundaries. So I'm sure you remember it from the Poisson equation solution that you can have the Dirichlet, we have the potential on the surface, or it can be the Newman, and then it's the gradient, which is the electric field. Yeah. It can be also for the heat equation. So if it's Poisson, this is actually what we have here is electric field. E on the boundary. If it is the heat equation, then the gradient is actually what we have here. F is the heat flux. Because the gradient of the temperature is the gives us the flux of the temperature, and yeah. Okay, so it can be X and T. If it is a Poisson, it would be X and Y. If it is a Poisson. Okay, so what we now, in order to write, to find the solution scheme, we need now to discretize in both time and space. So in Euler, it was only space, So we write it as, so the time we discretize as Tn is n minus 1 times tau, in space, we write as xn is something, oh, sorry. Now, in space, the index is usually I, and it would be the initial position, let's say xa, plus I minus 1 times h, which is delta x. Yeah, so we can describe it in the following way, that if we take, let's say this is t and x, so we have this grid, and so on. And we are given, so we want to find what is A, and we'll write the two indexes. Yeah. We can do it, it doesn't matter. A and I, which is a function of x, I, and t, n. So we are given the initial, so these are the initial values which are given, and these are the boundary values which are also given. And what we want to find is all the values in all these empty circles are the values which are trying to get in order to solve the temperature as a function of position and time, or electrostatic potential as a function of space, and various other problem. If it's, Poisson, again, it's going to be boundary values in both axes. And so let's go directly to the heat equation or the diffusion equation. Let's write it again. So we have the temperature. Which is a function, let's do it in 1D, d dt is k times the second derivative of t and x and t. And I guess you don't, have you seen this diffusion equation in some course? You remember it? No, okay.
Yes, it should be in semester 3 in learning PDEs.
Okay.
Learning course in PDEs.
Yeah, okay, exactly. So it's part of the course on PDEs, not so much in physics, but you derived it based on the fact that the heat flux heat flux is minus K temperature gradient. So that's very simple. The heat flow depends on the temperature gradient. And what is K? Physically, what is K telling us? Or what does it depend on? Okay, we have some material. So we are talking about, let's say, something. There is TA here, TB here, and so
Heat conductivity?
Yeah, so this is the basically the diffusion coefficient. Yeah, so the heat conductivity. So we have we want, so we have some temperature distribution along this rod, and now we are changing. There is, and now this would be time. So we want to know what would be, how the temperature is going to change over time when we know what are the temperature at the boundaries, or what are the heat fluxes at the boundary. So this would be T equals 0, this would be T1. So when we look at the element here, we know that the heat flux depends on the temperature gradient. Yeah, so there is some heat coming in and some heat going out. And on the other hand, the temperature, the change of the temperature with time is just the divergence of the heat flux. Because the difference between incoming and outgoing heat tells us what is the net change in the heat per unit volume here, and which change determines the temperature change. So when we plug F, this F into here, we get the gradient of the divergence is the Laplacian, which is what is written here. So these two equations lead to the heat equation. And okay, and now we want to write what is the, look at the numerical method. So we will use the FTCS, which is the forward in time. And the centered space scheme. Okay, so we have we discretize the space and time. The space discretization will assume the region extends from minus L over 2 plus I minus 1 times H. And the time goes Tn is n minus 1 times tau. And x a is initial one minus L over 2. The other boundary xb is at L over 2. So it means n, we have n points in space. in space. So it means that the H is L over N minus 1. And yeah. Okay, and so what we are trying to find, T, so this is the equation that we want to write, and so we know the boundary condition are yeah, we know T at all T0 at I. So this is the initial condition. And in space, the boundary condition would be T at 1 as a function of n, and T n as a function of n. So these are the two boundaries. So basically, so this is T I of 0. And here we have T1 of n. And here we have T capital N in function. And we are looking for all the things inside here. So the difference scheme is, okay, let's write it here. So we want basically what we are doing is what we call want to discretize the PDE. So turn it into a difference scheme. So dt, the left term, we write it as simply t of I at n plus 1 minus t of I at n over tau. So the temperature at the time step of n plus 1 minus the temperature one step earlier at n over the time step. And in this, the other side, we use now the centered space. So that's forward in time. We take the next time step minus the current time steps divided by tau. Here we use the centered space scheme, which, to remind you, the second derivative is, let's write it here. So it's t I plus 1 and plus t I minus 1 and minus 2 t I n divided by h squared. Yeah, so this is what we have on the right-hand side. So the scheme now, okay. Yeah, and I'm finishing in a minute. So basically what we have here, this is on the left-hand side, this is on the right-hand side. So what we have is that T I n plus 1 is T I n plus, we move tau to the right-hand side, plus k tau over h squared, and T I plus 1 n plus T I minus 1 n minus 2 T I n. So basically, we start at n equal 0. So we take basically 3 elements here, and so this is if this is I and n, so we actually take these 3 elements. This is I plus 1, this is I minus 1 and n, and the combination of these 3 plus this TIN together give us the next element of I n plus 1. So basically, given these values, we just have this very simple scheme that builds all the other missing elements based on the boundary and initial values. And what do we need to know about what is the demand if, let's say, we are given some h value, which is the resolution in space. So this is given. So what is what tau or resolution in time should we use? So can we use any time resolution, or is there some condition on the time resolution? Look at this equation.
Maybe tau and h square should be of the same order, perhaps?
This has dimension of temperature. So this is temperature. This is initial temperature. This is the final, so go for the next temperature. What would be a good scheme? So this gives us the change in the temperature. So actually, we can think of it, all of it here is the, so this is the temperature change. So if we want the scheme to be accurate, what do we want the temperature change to be compared to the initial temperature?
We should evaluate it with maybe with K, compare it to the coefficient.
So this is given. So K, this is given by the specific PDE.
Yeah.
Solving. By the characteristic, it's metal or wood or whatever, air. So we know the heat conduction. We now select some spatial resolution where we resolve the temperature. What would be the time steps we want to use?
We wanted the entire term k tau by h squared to be small, where small is defined by how accurate we want it to be. So tau needs to be some constant and then h squared times divided by k, maybe?
Yeah, exactly. What we want physically, we want the temperature change to be small compared to the temperature. Now, this coefficient, what is the dimension of this coefficient?
It's
Meters
dimensionless.
squared.
It's dimensionless because this is the dimension of temperature, this is temperature. So this has to be dimensionless. Dimensionless. So basically, and this is of the order of the temperature itself. So we want this coefficient to just be smaller compared to unity. So what we want is k tau over h squared to be much smaller than 1. How much smaller depends on the accuracy we want to calculate. So basically, it means the tau should be much smaller than h squared over kappa. So this is something very fundamental, that the steps in x and in both directions are related. Once we select some resolution in one direction, that implies some minimal value of the resolution in the other dimension, or here the time steps should be smaller than these values in order to reach a precise solution. Okay, so we'll continue next week. I'll put tomorrow the homework sets, which will be a bit more on the ODs and one first question on heat conduction. Yeah, so if you have any question, then just send me emails, and see you next week.
Thank you, Ari. Goodbye.
Bye-bye.
Thank you. Bye-bye.
Bye.
Professor, can I ask you a question if you have time?
Yeah.
So
yeah.
I have, actually I can show you the screen if you can let me. It's about Runge-Kutta 2.
Yeah, yeah.
So I am not sure if I understand this method correctly.
Which method?
Runge-Kutta 2.
Ah, yeah. This is actually the midpoint method.
Yes, exactly. So
yeah,
I did in the question, like I don't know if you can see it in the
yeah, I see. Yeah,
so,
I see.
So here, for example, so from what I understand, in the right side, you see these equations. I think these relate to the. I mean, these were the formulas that I used in the question.
Yeah.
So, for example, in the here, like for the next the velocity, I take the previous velocity from the previous time step, and I multiply. I add it with time step plus the acceleration from the previous time step.
Yeah.
And I continue in order to find the position in the next iteration. The previous x multiplied by time step divided by 2, and the velocities from the current and the previous iteration.
Yeah. Okay.
So I cannot see if I make a mistake in Runge-Kutta 2, because I couldn't get the results that.
This is in the third question. In question
yes.
3.
Yes.
Yes, this it looks like the correct expression. Yeah.
because so I cannot see where I made the mistake. So I can just a second. So here's the code. So what I do is basically, so this is the equation I just showed you, and I also calculate analytic. Actually, I just saw a mistake. So this should be I plus because I am calculating the analytical calculations. So I find x and v for in the iteration. Then what I do is I calculate analytical and numerical energies. And then I so what I do is I calculate the analytical and numerical energies at the end of the like 10T. So at 10T basically. So then I check the error value. You know, I divide I take the difference between them and divide it with the analytical solution.
Correct.
So why am I not getting the results that like I was expecting to get? I couldn't see it.
Hey, what did you get?
I get a much higher value than you were asking. In the for example, I can show you.
You mean?
So what I get was just a second. I am going to show you. So here, so you see the.
Yeah, right. That should be much smaller.
Yes, exactly. So, but when I look at the plots, I mean, it looks fine. I cannot. So I cannot see my mistake.
Okay, two analytical. So it seems like the solution is accurate, even though your measured value gives a low accuracy, right? Or, I mean, or in other words,
can you say that again?
The number, can you lower it a bit? Yeah, okay. What was in question 2? What did you derive for the relation between the error and the time step?
In question 2, for the Rangakuta, this one.
Yeah, right. This is correct. So what I suggest that you check just one time step. Okay, so run your the numerical solution for just one time step and see whether you get it satisfies what you derived analytically, because it should agree. And then once it agrees, now you can take 2 time steps and you can check following the derivation I made on the board in the beginning of the lecture and see, yeah, maybe I stopped, by the way.
Okay. Okay, then.
Oh, never mind. But so you see my point. That was also one of the reason I gave this first analytic derivation and then to do it numerically. So just verify that you get what you get analytically. Then you can, just check line by line. And you get
the I see your point. Okay. Okay,
so
then, thank you.
The way to debug a code is always to go to something very simple the simplest step you can make, which you can follow with a paper and pen and pencil, and then see it agrees, and then you go to the next step.
Okay. Okay, then thank you. Thank you.
Okay.
See.